Okay, so welcome back to lecture 8. This is a continuation of our little mini series on derivative rules. So before we continue on learning more rules, we should probably recall what we learned last time, right? So there were a few that are important. And this isn't all of them, but I think it kind of generalizes all of the ones that I wrote down. So any of the ones that appeared last time will be of one of these cases here. So the derivative of any constant is, come on guys, answer me. Zero, right? And our reasoning for that, we didn't derive it algebraically, but our reasoning was that the slope of the tangent line to the curve of any constant is just flat, right? And then part two, or not part two, rule two, would probably be the power rule. So the derivative of x to the power n is equal to n times x to the power n minus 1. Right? It's for any rational choice of n. Okay. And finally, there was the sum, and not finally, there's actually two more.
No, there's another one that you probably have missed.
Let's see, let me write down these two and see if I didn't catch that one. Okay, so derivative with respect to x of f of x plus or minus g of x is equal to f prime of x plus or minus g prime of x. And so maybe that takes care of two possible ones that I wrote down last time. And what else was there? Oh, there were the basic trig rules, right? So the derivative with respect to x of sine of x is equal to cosine of x. And then a part of this rule would be derivative with respect to x of cosine of x is equal to negative sine of x. Okay, so that's what I wrote down the very end of last lecture with these rules here. And your textbook actually has a nice derivation of these things. But again, and as always, I'd like for you to try to imagine why that's the case. In particular, for example, derivative of sine x is equal to cosine x, that one takes some thought to kind of convince yourself that that's going to be true. But if you start looking at the values of cosine of x as x increases and compare that to what you think the slope of the tangent line to sine of x is at a point, you'll see that, oh, this is making sense. Again, this isn't a proof, but it's just reasoning why that might be the case. Okay, so we have derivative of constants, power rule, plus or minus, and then these basic cosine and sine derivatives. Now, in this lecture, we're going to learn two more, only two more. And these will be the product rule and the quotient rule. So looking at derivatives of products and looking at derivatives of quotients. I have a question. What's your question?
We did the products and the constant. We did not do the
I wrote these down at the very end.
Yeah.
But we'll use them today. We did look at, good catch, the derivative of a constant times a function is a constant times a derivative. We did see that.
Yeah. And we also did derivative of x equals 1.
That, so say that one more time. We did,
Derivative.
so we have a question right now. So the derivative with respect to x of what?
x.
Okay. Now, if you remember a few minutes ago, I said that I might not write down every single rule, but I bet you everything that I wrote down from last time is one of these things, right? So which of the rules 1 through 4 does this fall into? The power rule. Why is that? Because if we look at the derivative with respect to x of just x, right? This is equal to the derivative with respect to x of x to the power 1, right? So what does this become? This becomes the n is 1, right? So it'd be 1 times x to the power 1 minus 1, right? And what does this become? 1 times x to the power of 0. What's any number raised to the power of 0? 1. So it's just 1, which is that, right? So this is like a generalization of that thing. Okay. And yes, I did omit one good point that you brought that up, by the way. The derivative of a constant times a function is a constant times a derivative. But we'll see that that's a special case of the very first rule that I write down now. I didn't do that on purpose. I did honestly forget it, but it is a specific case of this thing I'm about to write down. Okay. So theorem. So if f and g are differentiable functions, I'll just write differentiable for the sake of saving board space. So if f and g are differentiable, then the derivative with respect to x of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x. Okay. Now, especially for those out there that are not super comfortable with things as simple as order of operations, which when I took calculus, I wasn't comfortable with yet as well. You might try to take up too much space in your memory trying to remember that, looking at just like that, right? Like, is there anyone in class right now that would honestly try to remember it exactly like this? See, that's like what I would have done. So I'm assuming that at least someone would have done that because I was in your shoes. So, well, sort of a long time ago now, but I did that. I tried to just memorize exactly as the professor wrote it on the board. But pause. Let's think about what this is saying. The derivative of the product of these functions is the sum of a function and the other one's derivative. A sum function and the other one's derivative. Do sums matter? Is 1 plus 2 different than 2 plus 1? No, right? And then even the way that the product is 1 times 2 different than 2 times 1? So you don't have to remember this exact form, right? You could just say like, I literally could have wrote this, like f prime of x times g of x plus g prime of x times f of x. Same thing, doesn't matter, right? As long as you remember it's the sum of the multiples of original and derivative. And once you remember that, you are taking up less memory. Like this is harder to remember than that, honestly. So hopefully that's not too bad now. because there's like lots of symbols and equals and pluses. It's a lot. So let's go ahead and look at an example. So find the derivative of, what example do I have? Y equals to x squared times sine of x times cosine of x. Okay, at least in person, if that's intimidating, raise your hand. Okay, I like your honesty, right? So it's intimidating because there's a bunch of trig things, which a lot of you are probably rusty with, or never actually learned when you took pre-cal, just kind of made it through. There's a bunch of different terms, it's long looking, right? So it's understandable to be hesitant about it. However, if we break it down into its pieces, we should be okay, right? Now, there's many, many different ways to do this. The way that I'm going to do it is identify what in that product I know how to find the derivative of, right? Like if just this in the simplest form. So for example, like I know the derivative of x squared, right? So maybe I'll just write that out. So I'm most likely going to run out of room, but I'll try to fit it here. Solution. Now I'm going to be very precise. I'm going to say let f of x equals to x squared, or equals x squared. G of x equals to sine of x. And h of x equals to cosine of x. Okay. Now, do we know how to find the derivative of f? Do we know how to find the derivative of g? And h? They're like on the board behind me. We're good, right? Okay, so at least we know something, right? We know we can like compute something, right? So next up, maybe we can somehow use that product rule, right? Maybe. So, okay, let's try this. So derivative with respect to x. So I'm going to take the derivative on both sides of this thing. Okay. When I take the derivative of y, I'm just going to write this out for notation. This is notation. Okay. If I take the derivative with respect to x of y, we write that as dy dx. The derivative of y with respect to x is just notation. So if I apply the derivative as an operator, remember how I've always called it an operator. If I apply it to both sides of this equation, on the left-hand side, I get dy. And then on the right-hand side, I don't have to do anything yet. I just write this operator applied to these guys here. But instead of writing out all of that business, right, I know what the pieces are. I wrote them a different way. So I can write this as f of x times g of x times h of x. It's the same thing, right? Because I said in my solution, x squared is equal to f. times G times H, right? Now, this might seem like a lot, but I'm taking the thing and I'm breaking it into very, very small pieces that I can understand. So now, right, I have three functions being multiplied together, right? This rule here, the product rule, applies to two functions being multiplied together, right? So maybe what I can do is maybe treat, see if I can use a different color, like this right here is a function. And then that's the other function, right? I could do that, right? So then I could apply this rule. Derivative of that product of green times H is equal to H times the derivative of green plus green times derivative of H. Okay. So this is going to be, I'll use the same ordering. It doesn't matter what the ordering I put though. Again, please don't think the ordering matters. I can say, all right, f of x, g of x, that's my green guy, right? That's like here, like maybe I can use colors like, there's green, green, green. That's D green, this is the derivative of green, right? Times G prime, right? Green times G prime. The G's and the H's might be confusing to you, but you understand it's the second thing, right? Again, this is why saying out loud, like what the rule is saying, what the theorem is saying is important. It's the first function times the derivative of the second plus the second function times the derivative of the first. Whatever it is, it can be R, H, Q, it doesn't matter, right? So all I know is that this is the second function. So H prime of x. Right? That's the derivative of the second one times the first one, right? Is this okay? So then I have to add the second function times the derivative of the first. Hopefully I'm not going off screen. I think I still have some room. So this is the first one, I'm just going to put it in there. That's the derivative of the second. I don't know what it is. I just know that that's, according to the theorem, that's what it should be. So here's my green guy. And then here's my green guy here. I'm taking the derivative of it, right? So lots of writing, but I'm just every small piece. So the first part stays the same. H times this thing, right? Yeah. Now this is, again, the product rule. You see that? That function and that function, right? So what this will be is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. So all together, let's just like, we have to distribute now, right? It's that times that sum, whatever that is. So dy dx. Be very careful and write f of x times g of x and h prime of x plus distributive law, that times that, plus that times the second half. So running out of room. Let me kind of go down a line right here. Admittedly, there's lots of lines here. And it's because I'm being especially careful, right? I can write the solution like quickly, whatever, but I'm being very careful right now. Okay, just to illustrate a point. Like I make assignments here of functions. I look at it, I split it up to make it look like that. I apply that, and then I distribute in with algebra. That's the answer. It's not what your textbook like homework will accept, but that's the answer. Whatever those values are, we expanded everything correctly. This is it, right? We just have to, if we want to know the exact answer, we have to fill everything in. Okay. So maybe I'll erase this now. Make some room. So in your notes, if you're following along, all of this should be stacked neatly on top of each other, right? So we already know what F, G, and H are. F, G, and H. We already know what that is. We just now need to know their derivatives, right? So F prime of X is equal to what? Go ahead and tell me. 2x, using the power rule. And what's G prime of X? So G is sine, so the derivative would be cosine X. And then what's the derivative of H of X?
Negative sine X.
Negative sine X. Again, this is the complete solution here. Like anyone that's reading this could plug them in and then it would be something, right? But let's just go ahead and plug them in to get what it should look like. So then dy dx, I just have to fill everything in. So we have x squared times g. So that's x squared times sine of x times h prime, which is that. And then we have plus this other business. So we have h, which is cosine of x, times f, which is x squared, times g prime of x. So that's cosine of x. And then finally, the third term, we have h, which is cosine of x, times g, which is sine of x, times f prime of x, which is 2x. But again, This on its own is the answer. This together with that is more of the answer. It's more descriptive of what's going on. And then this is the complete messy form. I call it messy because there's just so much going on. It's not just three things, right? In this equation here, it's literally just three things. On that, you have all kinds of numbers being involved, powers, all sorts of stuff. So I could maybe simplify it. Yeah, I guess I can. So this is going to become, I can factor out an x. And then this would be minus x sine squared of x plus, oh. No, I can. I almost saw something, but it's not. There's a minus sign. So plus x cosine squared of x plus 2 times sine of x cosine of x. So what I did is I factored out an x from all of them. That's the only thing I could factor out. Okay. There's probably some more factoring because I see sine squared and cosine squared, but there's a negative sign, so I'm not going to bother with it. This is the answer. Whatever. Now that was an overly extended example, honestly. Okay. This is on the upper end of what your homework type of problems would be, like all this. You typically just have two functions, right? But I just want to get you into the practice, or at least like be aware of substituting things in, right? In fact, to make it like really simple to write, I probably should have just said f is equal to x squared, g is equal to sine x, and h is equal to cosine x, without writing the x emphasizing a function. And then all of the notation would have worked out. It just would have been shorter to write. Okay. So again, this is one way to write the solution. Another way would just be to know how it's going to, no, this is probably the safest way. I'll show you another way, right? I encourage you in your notes, though, that to try the following and see if you get the same answer. Here, we chose this to be the first function, right? We could have easily have chosen f to be the first function and g times h to be the second function. Would the answer be the same? It should be, but you should verify it, right? It's like an exercise to try. It might be like a bonus problem on an exam. Yeah. There was only a factor of 1x there. And I took that out, which is now out there. And now the only coefficient.
So if we were to put x times 2 sine x cosine x, won't that be 2x sine x squared?
Yes. Why would we multiply it by x?
I mean, like,
Oh, no, I took it out, right? Not there anymore.
oh,
I took that x out. I took 1x out, 1x out, 1x out. So notice the x squareds now are just x, and now that x is gone.
okay.
I just factored them out. Yeah. Just probably other factoring that I could do, actually, but I don't want to go through that process right now. Okay, so rather hard example. But let's try another one where I let you work on it for a minute. One that's not as hard. Find the derivative of y equals to x cubed times x. Okay, and I'm going to pause the recording for 5 minutes. Okay, so this is a simpler version of what we just did, and it's just an application of this product rule that I wrote as a theorem. So let's look at the solution. So we're going to apply the derivative as an operator on both sides of this equation, which means that dy dx is equal to the derivative with respect to x of x cubed times cosine of x. Okay. Now identify your functions here. Like if you were to split this into two functions, what would be what?
F of x would be x to the third.
So we can say like, we can even say that up here if you want to be very specific, like I was last time. And then g of x would be cosine of x. So then we have derivative of a function times a function. Okay. Now, again, when you think about the product of functions, it's the first, it's just the sum of function times derivative of the other. That's it, right? So I can just write this out as like, I don't know. There's any, like the ordering doesn't matter, right? Maybe I'll just do it like this. So x cubed times the derivative with respect to x of cosine of x plus cosine of x times the derivative of x cubed. So then what's the derivative of cosine? It's negative sine, right? So on the left-hand side, we'll have negative x cubed times sine of x. What's the derivative of x cubed? 3x squared. So on the right-hand side of the sum, the plus symbol will have 3x squared times cosine of x. And that's it. Okay. Now, we've just been applying this theorem kind of blindly. Why would it make sense for this to work, right? Like, why is it that it's the derivative of one times the other plus the derivative of the second times the first? Like, why is that sum making sense? Well, if you think about something that looks like this, right? Like if you, right, like if this is like somehow you're getting like some y values from, like some product of functions, right? Now, what is the derivative measuring, right? It's measuring the slope of the tangent line at a point, right? But it's also kind of measuring what this like change in y over change in x as the change in x becomes very small, right? Like how much is the y value changing? Right? So how much is the y value changing, right? Well, it's kind of maybe proportional. What does this word mean to you, proportional? Like proportional to some values, like a number times it, right? Like that's what it roughly means. So it would make sense that the change in y for this thing depends on how fast that one's changing and also on how fast that one's changing, right? As x like gets really small, the differences in y's are approaching some value, right? So it's happening for both of them simultaneously. Now, so it makes sense that we would need the derivative of both of them if we're going to look at the derivative of the product. So it makes sense that, yeah, we would at least see two derivatives. But why is it this way? Why is it derivative times one function plus the other derivative times the other? Well, it's conceptually, think about how this function is growing on its own, and then how the quote unquote instantaneous rate of change of this one is growing. Right, the growth in one hand is kind of the derivative of that times the original value on one hand of it, right? But then also the instantaneous rate of change of this one is affecting the growth of that one. It's like scaling it up or down, right? Cumulatively, it's the sum between them. Now, this is not a mathematical proof, but that's a general idea of what's happening. It's how fast are these, like together they're multiplying each other, right? So if this one's changing really fast, and that's like the derivative, then it's going to scale.
لا لا
The scale how that one's changing, which is like the derivative again. And then together it's just the sum. Or if it was a difference, it would you'd be subtracting, not the difference, but together it's just the sum. Okay. So that was like a brief kind of vague intuition behind that. Now we have a second theorem we need to consider. So if F and G and G, yeah, G is differentiable. I'm tired of writing that out, so I'm going to just do diff with a dot. And G is differentiable at all values x with or where G of x is non-zero. And the derivative with respect to x of the ratio of f of x over g of x is equal to g of x times f prime of x minus f of x times g prime of x all over g of x Now, this one is a little bit harder to kind of justify why this would be the case. And I don't even want to ask you because I wouldn't imagine that you'd be able to justify why this formula exists. Well, can't we rewrite this guy right here? Isn't this thing the same as saying the derivative with respect to x of f of x times g of x to the power minus 1? Isn't it that the same thing? Now, does that help us at all? We don't have the necessary tool to really nail down almost a proof it's true, but can we at least like reason about it a little bit? So we know how the product rule works, right? We could apply the product rule of this to this. This is a product of two functions, right? So, okay, if we look at it, doesn't the top sort of look like the numerator? Doesn't it sort of look like the product rule? I mean, function times derivative. There's a minus for some reason, but then the other function times the derivative of the other one.
Isn't the minus because instead of multiplying, we're dividing?
Well, that's I'm trying to explain it though, right? Like if we're thinking of only the product rule and not this formula, we're kind of trying to figure out why, right? What happens when you apply the power rule to something like this? What is this derivative?
Negative x.
What's the n is -1, right? So it's n times x to the power n minus 1. So it'll be
Negative.
n times x to the power n minus 1.
So it's negative x to a negative 2.
Exactly. Negative x to the negative 2. Okay. So notice there's a negative there, right? So there's like a negative right there, right? In a sense. And then one more thing, and again, this is just a vague kind of reasoning for that formula based off of the product rule and not what we really need. If I rewrite this, what does this become? -1 over x squared. So if our g was x, right? We see all those terms appear. This is like, if we replace x by g and we just kind of try to take the derivative of it without the rules that we need, we see that there would be some type of minus there, and then we see that it would appear in the denominator with the 2, with the power of 2. We'll actually talk about this more next lecture when we introduce our final derivative rule. But for now, take it as is. And note that unlike the product rule, this ordering does matter. Right? Like 1 minus 2 is different than 2 minus 1. Right? So it's your denominator times the derivative of numerator minus numerator times derivative of denominator. Okay. And again, if you forget that there's a minus, like which one goes where, just imagine you write 1 over g of x as g of x to the power of -1 and think about the product rule again, you'll see that that's why there's a minus there. Sort of. Okay, so let's do an example. Find the derivative of y equals tangent x. Y is equal to tangent x. Now, you might be confused because that doesn't look related to something that looks like this. It's not it doesn't look like a ratio, right? But what's the definition of tangent? Sine over cosine. So it actually does look like that. So if I take the derivative on both sides, now, for simplicity, let's assume that this part is satisfied, meaning that we're considering only x values where cosine of x is not equal to 0. Right? So that's excluding what? Pi over 2, any multiple of pi over 2, any whole pi over 2 plus pi over 2 plus like all that sequence we did one of those lectures in the past. Okay, so assuming that we're in the correct domain here, let's just apply this rule. So this is equal to the denominator times the derivative of the numerator, which is derivative of sine is just cosine, right?
Cosine.
Minus the numerator times the derivative of the denominator. All over cosine squared. That is the solution. But again, this isn't how it would appear as an answer choice. Because you have to like multiply those together and then maybe something nice will happen.
Does the trig identity cosine squared plus sine
It
squared,
does apply in about one more line. What?
does it apply in not squared?
No. It has to be, which I'm about to mention this identity here in a moment. So let me wrap this equation back over here and I'll mention exactly that. So if I multiply those cosines and sines together and then the minus times the minus becomes a positive, I get this. I get cosine squared x plus sine squared x all over cosine squared x, right? Cosine times cosine, cosine squared, minus sine squared, minus and minus sine squared is plus sine squared. So there's a very important identity from pre-cal and trig that sine squared theta can be anything, it can be x, whatever, plus cosine squared theta is equal to 1. They all recognize that? You know, this is also like, this is related to one of my favorite equations that I kind of was bummed that y'all didn't know a few lectures ago. Right, x squared plus y squared is equal to the radius squared. X squared plus y squared is equal to the radius squared. So this is describing a circle of radius 1. It's a unit circle. That's why it's true. That's how you can always remember it. Sines y, cosines x, square them, you get equal to 1. That's a circle with radius 1. So this numerator here is exactly that. It's equal to 1. But we're not done. Why do you think I wrote that? It's the same thing, right? 1 over cosine x squared is equal to 1 over cosine times 1 over cosine, which is 1 over cosine squared. What is 1 over cosine? Secant, right? 1 over cosine is secant. So this is really secant all squared. So the derivative of tangent x with respect to x is actually secant squared x. Whenever you're considering a domain where it's defined, where cosine is not equal to 0. Okay. Now there are a few other derivations that we could look at. But I'll just give them to you as a table for the rest of the trig functions that you can derive. Like cotangent, you can do the same thing to find the derivative of cotangent because that's cosine over sine. Right? Now, I think that just shows an application of it. So that type of problem And because my foot is really bothering me, I think that'll be it. Like I said, it might be a short day. Next lecture, I'm going to do specific applications of these two rules, as well as introduce the final derivative rule that is the most important. At least like to me, it's the most important. So thank you all for joining, and that'll be it.